Hi friends, today we are going to talk about UV visible spectrometry or spectroscopy. That's one of the most important spectroscopy these days. So UV visible spectroscopy is an absorption spectroscopy or reflectance spectroscopy in the ultraviolet visible region. It means it uses the light in the visible edges and the adjacent ranges. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. In this region of the electromagnetic spectrum, atoms and molecules undergo electronic transitions. So the main principles involved in the UV visible spectroscopy can be said by electronic transitions. Electronic transitions from molecules containing pi electrons or non-bonding electrons, which can absorb the energy and in the form of UV and light, and it excites to the higher antibonding orbitals. And the four possible configurations are sigma to sigma star transition, pi to pi star transition, N to pi star transition, N to sigma star transition. But there are 6 actually, but the 2 of them are just theoretical transitions: sigma to pi star transition and pi to sigma star transition. As it is clearly shown in the slide which I have made, the principle of UV spectroscopic process is very clear. In UV spectroscopy, the sample is first irradiated with the hot spectrum of the UV radiation. Then, if a particular electronic transition matches the energy of a certain band in UV, it will be absorbed. Then the remaining UV passes over the sample and it is observed. From the residual radiation, a spectrum obtained with gaps at these discrete energies. This is called absorption spectrum, which we have studied in plus 2. Now let's take a deeper look at each of the transitions. The first one is sigma to sigma star transition. So the sigma electrons from orbital is excited to corresponding anti-bonding orbital sigma star. So a large amount of energy is required for this transition. So basically alkanes which having CH bond only can undergo sigma to sigma star transition. And the absorbance maxima shown in the example is at 125 nanometer. So the next transition is pi to pi star transition. So whichever compounds which have this pi electrons can undergo this transition. So the bonding orbital is excited to corresponding antibonding orbital. The compounds like which contains multiple bonds like alkenes, alkynes, carbonyl, nitriles, aromatic compounds, etc. undergo pi to pi star transitions. Alkenes are one of the main examples as shown. Now the N to sigma star transition. Saturated compounds containing atoms with lone pair of electrons like oxygen, which is having 2 lone pairs, nitrogen, sulfur, and halogens are capable of N to sigma star transition. This actually requires less energy than sigma to pi star transitions or sigma to sigma star transitions. So the number of organic functional groups within N to sigma star peaks in UV region is small. And N to pi star transition, an electron from non-bonding orbital is promoted to anti-bonding pi star orbital. Compounds with double bond and heteroatoms undergo such transitions. Now the 5th and 6th is actually this theoretical transitions observed. The UV spectrum is only of a few mode of absorption. UV visible spectrometry is used for many applications in medical field and to find compounds in organic field. It's used, and I have used it in one of my projects to find the silicon nanoclusters in silicon with silicon carbide. So the interesting part is from the UV visible spectrometry we will get the absorbance, which is plotted against the energy. From that graph we can calculate the absorption coefficient. So there's another graph called the Toc plots, which is made from this absorption coefficient and graph which shows the peaks at different values, from which we can calculate from which we can analyze where the silicon nanoclusters have been formed. That was my project, and thank you.